Okay, so the last couple of things we've talked about, there really wasn't a lot of homework on because it was mostly vocabulary and stuff like that. So today we're going to get into some stuff that we actually can calculate, and we can get some numbers and formulas and all that good stuff. So we need to talk a little bit about what's called data distributions. A statistical distribution is nothing more than a graphic or something summarizing the values within a set of data. For example, let's say we're going to do test scores. And let's say the lowest test score in the class was a 58 and the highest test score was a 98. And you have this number line marked out with all the possible scores in between. And you put a dot above the score whenever a student has that test score. Say 3 students had the same score there. And what happens is you put these dots in, you get what's called a distribution. If you take a line and you kind of follow it like that, the height of that line represents the number of items, in this case the number of students in that sample that took on that particular value. A typical distribution of numbers looks like this. A lot of you have probably heard that referred to as the bell curve, or just the grading curve. The technical name for it is called a normal curve. It's called a normal curve because that is the shape that values in nature tend to take on, normally take on. For example, if you wanted to do the height of people, you would have a number line down there representing their height in inches or centimeters or whatever, and this would represent somewhere in the middle. There's an average that has the highest number of people that have that height, and the further you get away from that average height, the fewer people that are, there's fewer people that are really short or fewer people that are really tall. So when we're talking about this distribution, there's 2 ways to describe it. One is center. For this current curve, the center would be right there. But I could create another curve. Oops. Like that. It is pretty much the same shape if I could draw better, but its center has moved over to here. So its center has moved. So it's one of the things that can change about these curves is their center can move. And we'll look at different ways to describe their center. The other thing we can look at, if we go back to this original blue curve, we can have a curve that has the same center but is narrower, like this one. Or we might have one that has that same center but is wider. Like this one. That is what we would refer to as spread. So let's look at ways that we can quantify center and spread numerically. Measures of center. To do this, I'm going to set up a little list of numbers for us to work with. It's a very small list, and realistically a list this small, it wouldn't even be worth doing a whole lot with because you can look at it and see all the numbers. But I'm just going to throw out 19, 16, 21, 25, and 24. So there's a list of numbers. If I want to evaluate the center of this, one thing that I can use is something called the mean. Now the mean is what most of us have always been taught is the average of a set of numbers. To find the mean, we take all the numbers and we add them up. So 19 plus 16 plus 21 plus 25 plus 24. Divided by, and then we divide by how many there are. There are how many numbers in this list? 5. So if we add those up, what do we get? We get like 105 divided by 5 is 21. Is that what you guys get? Somebody punch that in and double check me. Now when you're punching these in your calculator, by the way, as you're adding up, when you add 24, before you divide, make sure you hit equals first and then divide it by 5. Otherwise, it'll screw it up. It'll just divide the last number by 5 and add it to the rest of the list. As one of you are getting your calculator out and punching that in, one thing that comes up here, the 5 here, so that's the number of items in the list, that is referred to as little n. N is equal to the number of items in the list. So in this case, n equals 5, because there's 5 items in that list. Was that correct, Cody? Thank you, sir. The second measure of center is called the median. The median is literally, physically, and numerically the middle. So to do the median, we have to take 2 steps. Step 1, we have to put the numbers in order. So let's do that. We're going to take these numbers. It's actually going to be 16, 19, 21, 24, and 25. They're now in order. Step 2, excuse me, is going to be find the location of the median. So the location of the median, you take n, which in this case is what? 5. So n times 1/2 or n times 0.5. So 5 times 1/2 is going to be 2.5 or 2.5. If that is a decimal, you round up. So what that is telling us is that the median, 2.5 would round up to 3. The median is the third number in the list. 1, 2, 3. The median is 21. In this case, the mean and the median were the same number. In a well-distributed set of data, they will be the same. The mean and the median will be the same number. Now, that doesn't mean they're always going to be the same, because most sets of data are a little bit what we call skewed, and we'll talk about that in just a little bit. Now, I said if this is a decimal, we round up. What if it wasn't a decimal? Let me give you an example. I'm going to put up a totally different set of numbers now, and we're going to find its median. So this is a totally new example. And I'm going to start by putting them in order so that we don't have to put them in order. So in this case, step 1 would be to put them in order. We've already done that. What's step 2? Okay, so what's n here? 6 times 1/2, right? Times 1/2 or 0.5. N times 1/2. So 6 times 1/2. Everybody knows where the 1/2 comes from? The 1/2 is because the median is in the middle. The median is halfway through the set of numbers at the halfway point. So you could, for a small data set like this, that would work. But if you had a really large set, like 200 or 230 or whatever, that would be really tough to do. But yeah, that's the way a lot of times they'll teach you in high school. You cross off the first and the last and work your way into the middle. Yeah. So anyway, we get 3 here. Since this is a whole number, that means it is between that one and the next one. So we came up with 3. That means our median is between the third and the fourth number. 1, 2, 3, 4. So it's between 13 and 15. Perfect. To find out what's between them, we add them up. We average them together. Add them up and divide by 2. Again, before you divide by 2, what do you make sure you do? You hit the equals key. Then you divide by 2. That's going to give you 14. Otherwise, if you just do 13 plus 15 divided by 2 without hitting equals, it divides the 15 by 2 to get 7.5 and adds it to the 13, and there's no way 21 and a half is between 13 and 15. So you got to be careful with that. So that is the median. Yeah, go ahead, Cody. Yeah, not in our number system. Someday when you rule the world, you can make up your own number system, right?
I already have a nation.
Okay. The third measure of center we're going to talk about. Something called the mode. The mode is not a great measure of center. What the mode is it's the one that occurs the most often. Now, in both of the data sets I had, no number appeared more than once. So those have no mode. Many data sets don't have a mode. Sometimes you'll end up with two numbers that will appear the same, maybe you have two numbers that both appear 3 times. Some books will allow you to have, two modes. They call it bimodal. Other books will look at, okay, well, if you have enough items in the list, you can have more than one mode. For our purposes, there is one or none. Now, both of the data sets I've put up so far, there's obviously none because there's no number that was repeated more than once. But if you have a larger data set, is usually where the mode comes into play more. Then sometimes you'll have, like I said, 2 or 3 different numbers that all appear a lot of times, the same number of times. For our purposes, that would be no mode as well. Then there's a fourth one. There's actually several other measures of center out there, but some of them they're very quick and easy, and they're not worth mentioning. This fourth one is getting close to that range, but it's worth bringing up just a little bit. It's called the mid-range. To do the mid-range, we need the minimum, which is the smallest number, and the maximum, which is the largest number. Let's just go up to this list up here, because this we had both the mean and median for. The minimum is 16, the maximum is 25. So the mid-range is found by adding the minimum and maximum and dividing by 2. In other words, you're averaging the minimum and the maximum. That's 41, so you get 20.5. Now again, this is a relatively well-distributed set of data. You notice we had a mean of 21, a median of 21, and a mid-range of 20.5. So that's a pretty good set of data, well-distributed. Yeah, go ahead. Nope, 20.5. We're going to leave it as that. Assume this is a nice symmetrical bell curve here. In that case, the mean the median and the mode would all be the same value. Now, off the distribution curve, the mode is pretty easy to find because it's just going to be at the highest point up here. Where the curve is the tallest, that's the value that is taken on the most. So it's pretty obvious that the mode is at the highest point. The mean and median should be the same value if it is a well-distributed set of data, if it's truly normally distributed. But in real life, things are not always normally distributed. They are skewed. This is one that would be called skewed left. Because the longer tail off to the left. And this is one that would be referred to as skewed right. It's got the longer tail off to the right. And in all of those, you can see the mode is this highest point, right there or right here. Now the median is always the middle value. The median would move over a little ways from the mode. They wouldn't be at the same point. When it's skewed left, the median is to the left of the mode. Skewed right, the median is to the right of the mode. I'm just color coding right now instead of writing in the numbers, or writing in the words. So the green is the median. Of course, my mean is blue. The mean gets pulled out even further depending on how skewed it is. The question always comes up, what is the best measure of center? The mid-range, I already said, is kind of a secondary one. The mode, I've already kind of expressed my opinions on the mode not being really useful. So apparently we're probably down to the mean and the median. So in the battle of mean versus median, which one do each of you think is the better measure of center? The mean? What did you say, Cody?
You're adding up all the data.
Okay. And most people will say that. I was the same way. Boy, that mean it's just satisfying. You have a formula, you add them up and you divide. You're cranking out. You're doing math. It feels satisfying. But let me give you an example. In 1982, this also kind of goes along that lines of deceiving statistics that we talked about last week. University of Virginia. Advertised that the average starting salary of a four-year marketing graduate, in other words, a bachelor's degree in marketing, was, anybody want to guess? Just over $78,000 a year. Now, think about this for a second. That's 1982, which was 33 years ago.
That was, where is the last?
In 1982, the average starting salary for a high school teacher was between $16,000 and $18,000. So compare that. $78,000 was a lot of money. Heck, right now, $78,000. I would leave here for $78,000 a year. That's a good paycheck. But one thing that they did not disclose, that was the true number. That was real. But what they didn't disclose was one of the people who graduated that year with a four-year or bachelor's degree in marketing was a man by the name of Ralph Sampson. Now, Mr. Sampson was 7'2", and both his junior and senior year of college had been named the NCAA Basketball Player of the Year. Guess where he went after college? Played pro basketball. He was drafted number 1 by the Houston Rockets. Multi-million-dollar contract. In fact, Mr. Sampson was the only person in that group that made more than $33,000 that year. Only person in the group to make more than $33,000. It takes a lot of $20,000 a year marketing graduates to average out a multi-million-dollar contract to $78,000 a year. In fact, if you took his contract out of that, the average fell down to about $24,000 per year. So let me show you why that happened. Let's put in a list of numbers down here. In fact, let's go up here. I'm going to take this list of numbers right here. We already know that their mean is what? 21. The median was what? 21. Good. So now I'm going to make a second list of numbers. And first thing I'm going to do is I'm going to use these same numbers right here, and I'm just going to put them in order. We know that has a mean of 21, but I'm going to add another number to it. Right there. Now, when I go to find the mean, if I add all those up, what do I get? I get 190. And of course, it's going to be divided by 6. So that's going to be what? 31.67 is now the mean. The median, however, what's step 1 to finding the median? They're in order, right?
Yep.
Step 2 is n, which is 6 in this case, times 1/2, which is 3, finding the position. When I get 3, when I get a whole number, what do? It's between that one and the next one. So it's between the third and fourth number. So between 21 and 24. So I add 21 to 24, which gives me 45, divided by 2 is 22.5. So notice, when I added this single number, 85 here, the mean went from 21 to 31.6. The median went from 21 to 22.5. That one really large number, which is called an outlier, One unusually large and unusually small can do the same thing. Change the mean by a lot. In fact, there's the new number, the 85, is the only number in the list that is bigger than the mean. Everything else is smaller. The median only changed a little, and there's still half of the numbers are smaller than it, half the numbers are larger than it. So in statistics, it is generally accepted that the median is a more stable number. It does not change due to those extreme values or outliers like that. Does that make sense? I love this example up here because this is a wonderful example of how real statistics, real numbers, can be used honestly. I mean, that's an honest number calculated from the actual data, but still unethically, still deceiving. You don't often hear the word honest and deceiving in the same sentence, but this is one of those true cases where that is the actual number you get. It's still used in a deceptive way.
If you added another one on
Like a really small number down here, you mean?
yeah.
It would balance it out? Yeah. I mean, it's... Like I said, my main point of these last couple of weeks is not that you guys are going to walk out of here being just aces at doing statistics, because you're not. You're not going to have enough time to really get a lot of it. But it's to point out stuff like that so that when you guys see statistics or hear statistics being used, that you can at least know enough to question some of the things that are going on, just so that you don't get totally fooled by some of that. Okay, so we've talked about measures of center. Next, we need to talk about measures of spread. So the width of that curve. One of the measures of spread that we have is something called the range. Well, similar to the mid-range, the range, I'm just going to take this list of numbers again. Put them right down here. The range just involves the minimum and the maximum. So here the minimum, again, is 16. The maximum is 25. The range is the max minus the min. So here that would be 25 minus 16 would be 9. We have a range of 9. But now realistically, I'm going to put these numbers in order again, just because there's a lot of things you can see better when they're in order. That list of numbers has a range of 9. But I'm going to put another list of numbers up here that also has a range of 9. It also has a mean of 21 and a median of 21, just like the first list. But would you say that those are equally spread out? No. I would say the bottom one is a lot less spread out, because most of the numbers are right in the middle there. So we need a way to describe the spread of this to show that it is more spread out than the other set. So I'm going to, using this first set still, I'm going to define a measure called the standard deviation. Now there's a formula for the standard deviation. I am not going to try to confuse you by showing you the formula. I'm going to lay it out in a 6-step process. There are 6 steps to finding our standard deviation. Step 1 is to find the mean of the list of numbers. So for this list of numbers, what's the mean? 21. We've already found that, right? Step 2 is to subtract the mean from each. So that means, I'll take my list, 16, 19, 21, 24, and 25. I'm going to subtract 21 from each of those. Exactly. 16 minus 21 is a negative 5. 19 minus 21 is negative 2. 21 minus 21. 0. 24 minus 21 is 3. And 25 minus 21 is 4. Now at this point, it's not part of the calculation. It doesn't do us any good. But if you wanted to double check, just to make sure you're doing okay, if you were to add these all up, these numbers should add up to 0 at that point. If you had to round your mean, then it might not quite exactly equal 0, but they should be 0 or really, really close to it. Step 3 is to square those numbers. So negative 5 squared. Now remember, I've got the parentheses around the negative 5 on your calculators. That might be important as well. Because many of your calculators, if you try to square negative 5 without the parentheses, it will try to tell you that the answer is negative 25. Is the answer really negative 25?
No.
No. Any number squared must be positive. A negative times a negative is still a positive. So when you square it, you must get a positive result. So the negative 5 squared is 25, a positive 25, not a negative.
Wait, so then could you just go 5 squared and know that it's...
Yeah, you could. You just leave the negative off. Negative 2 squared will be... Oh, what's 2 squared? Is 4. We're good. 0 squared. 0. 3 squared. 9. And 4 squared. Why did I put parentheses around these last few?
You don't need that.
Yeah, they're positive. I only need the parentheses around the negatives. Good. Step 4. You know what the word sum means? Sum means to add them up. So I have 25, 29, 0, 38, 54. They add up to 54. Is that what you guys get? Okay. Step 5 is divide by n minus 1. In this problem, what's n equal? 5. There's 5 numbers, right? N equals 5. So n minus 1 equals 4. So I'm going to divide by 4. So 54 divided by 4 is 13.5. Now that number right there is important in itself because that number is often referred to as the variance. If we were going on in the statistical analysis talking about confidence intervals and hypothesis testing and relations between variances and ANOVA testing and chi-squared and all that good stuff, which would be like 13 weeks into a full semester statistics course, the variance would be a huge number for us. So I'm just putting that out there so you know what it is. But we were talking about standard deviation. And to do standard deviation, you need one more step, step 6, which is square root. Square root is this thing. The square root of 13.5 is going to be 3.67. That is the standard deviation. Now I'm going to point this out because a lot of people make this mistake. The square root, remember, is this symbol. Squaring is this times itself. A lot of people in their notes need to make that very clear that in step 3 you are squaring it. You are multiplying it by itself. In step 6 you are taking the root. Let's take a look at this list of numbers. Oops, you guys need help? Let's get the square root to work. You use second key, then your x squared button to do the square root.
So for number 6, then I'm doing what?
So you've got the 13.5, right? So you're going to do shift or second.
Second.
The x squared key is your square root key.
Right.
And then 13.5.
Okay.
Hit equals, it should be 3.67. So now let's do another set of numbers. I modified this set of numbers just a little bit, and you'll see why in a second. But you guys walk me through the process. Let's find the standard deviation for this set of numbers. Where do I start? Step 1 is what? Find the mean. So 16 plus 21 plus 21 plus 22 plus 25. Divided by 5, we get should be a mean of 21. Yep. Divided by 5, then it'd be 21. So we've got a mean of 21. What's next? Step 2. Subtract from the mean from each. So 16, 21, 21, 21, 22, 25. Minus 21 is 16 minus 21. 5, 21 minus 21. 0, 21 minus 21. 0, 22 minus 21. 1 and 25 minus 21 is 4. Again, those should add up to 0. We don't need to do it, though, because it doesn't really mean much to us. Step 3, square it. So negative 5 squared, 25. 0 squared, 0 squared, 0, 1 squared, 1 and 4 squared is 16. Step 4. Step 4 is to sum them. If I add those all up, I get 42. Step 5. Is divide by what? N minus 1. What's n? So we're going to divide by n minus 1, 4. N is 5. We're going to divide by 4. 1 less.
Oh, I thought we were still on.
No. If n is 5, we've got to divide by 4.
So n is 5 because there's 5 numbers, but if there were 6 numbers, n would be 6.
Yeah.
Right?
Yeah, n is the number of numbers in the list.
And so that 1 is always going to be 1.
It's always 1 less than that at this step in the standard deviation.
All right, okay.
So if there were 6 numbers in the list, you'd be dividing by 5. If there's 20 numbers in the list, you're dividing by 19. You're by 999,999,999. And then you're going after your math teacher for giving you that large of a problem. So you divide that out, you get 10.5. Step 6 is square root of 10.5, which is 3.24. You got it. There's a standard deviation. Now that number is smaller. We had 3.67 up here. So that does tell us that that list of numbers is less, even though it has the same range and the same mean as the other list, this list is less spread out, has a smaller standard deviation. What do you guys think? Now there are other measures of spread in position, things like quartiles, we'll talk a little bit about on Wednesday. Percentiles. Percentiles, once you understand percentiles, we'll probably do the percentiles first, because once we understand the percentiles, the quartiles make a lot of sense. But they're really easy from percentiles. And percentiles is one of those things you're going to hear about your whole life. You talk about maybe your child's weight and the doctor says he's in the 78th percentile or whatever. What does that mean? Well, to say that they're in a certain percentile, let's say they say that they're in the 78th percentile. What that means, if we're talking about their height or weight or whatever, that they are, if we're talking about their weight, we're saying that they are heavier than 78% of all other children in their same age group or in whatever group that they're in, whatever classification they're in. If you're looking at your standardized testing that you get in school, if they tell you you're in the 57th percentile, most people, if they were told that they took a test and they were in the 57th percentile, they'd feel pretty bad. They'd think they didn't do very well. But 57th percentile, what does that really mean? Yeah, you're better than 57%. You're better than more than half of everybody else. Not a lot better. You're pretty average, but you're on the maybe on the slightly upper end of average. Is what that's telling you.
So if you were in 78th percentile,
You're doing okay. You're better than 78% of people at that particular thing. I mean, I'm not. You know what I'm saying? At that particular skill or whatever that measure, you're measuring that weight or height or whatever. You know, if you're at the 50th percentile, that means you're exactly average. So you're right in the middle of the road.
100 percentile is good in some ways, bad in others.
Well, yeah. Yeah, it depends on what you're measuring. There should be a new quiz due tomorrow. And a new homework due for Wednesday. Wednesday, we will take a little time. There's a couple more things in statistics I want to talk about. And then we will take time to review for the unit test. Thursday will be unit test. Next week, Monday, we'll take a little bit of time to review for our final test. Not a lot. I mean, the final test is, like I said, more to see what you remember, see what you've really learned from the course. It's not really to evaluate you. If you do really, really well on the final test, it can help your grade. It cannot hurt your grade. Unless you don't take it. You will be penalized if you don't take it.